Problem number 17 sometimes had an issue because it has an A for a base. But what we're doing is we're going to solve for x. And the first thing that we need to identify is what property are we going to use on the left side of the equation. And what we see is we see that there's a plus right here, and when we have a plus, that means that we can rewrite this problem by multiplication. We can rewrite that left side by multiplication. We can take x and we can multiply it by x minus 2. And then we still have log base a on the right side. And now, since we have log base a on the left and log base a on the right, we can, so to speak, it looks like we're canceling out the log base a's, but we're not really canceling them out. We're ignoring them. We don't need them to help us solve. We need where the variable is, which is the x, is x plus 2 equals x plus 4. And maybe the fact that it was base a instead of some number was the issue on this problem, but now we're going to distribute and get x squared minus 2x equals x plus 4. And we're going to have to factor eventually. So let's move the x over to the other side, and let's move the 4 over to the other side. And we get x squared minus 3x minus 4 equals 0. So now, we can factor this expression. And we need the factors of 4 that combine to be 3. And 4 times 1 is 4, and 2 times 2 is 4, but the only way that they're going to combine, which means that they're going to add or subtract to be 3, is with the 4 and with the 1. And it's going to be negative 4 and positive 1. And now I hope that you can tell me that the answer is x equals 4 and x equals negative 1. But if you need to, it's x minus 4 equals 0 and x plus 1 equals 0. We add 4 to both sides. So we get x equals 4. Subtract 1 from both sides, we get x equals negative 1. And after all of that work, we still need to go back and check for extraneous solutions. So we go back to the original problem. And what we're looking at is this part of the logarithm right there. This part of the logarithm. This part of the logarithm. Sometimes called the argument. Those values have to be positive. And if we ever find a negative value there, then that's going to be an extraneous solution. So we come down here with the 4. 4 is positive. 4 minus 2 is positive. 4 plus 4 is positive. They're all positive. So 4 is a solution to this problem. Negative 1, however, is not going to work because log base a of negative 1, we cannot figure that out. This is negative 1, and that value needs to be positive, which means that negative 1 is going to be an extraneous solution. Problem number 4. What we need to do is we need to look at the coefficients on the logarithms. And we're going to apply the properties to our logarithm. So we're going to take this value of 1/2. We're going to make it an exponent. We're going to take this 2. We're going to make it an exponent. And that's going to happen on problem number 3. It happens on problem number 4 as well. So we end up with log base 3 of x to the 1/2 equals log base 3 of 2 squared. And what we've accomplished is we have log base 3 on the left, and we have log base 3 on the right. We don't need that to solve. So we're going to ignore the log base 3's, and we're going to solve x to the 1/2 equals 2 squared. And what might have caused trouble on this one, aside from the fact that there was a coefficient, is how do we deal with x to the 1/2? And remember that all that x to the 1/2 means is it means the square root of x. The denominator of the fraction goes in the check mark part of the radical, but we don't have to write that down. And over here, 2 squared is 4. Well, we want to know what x is. We don't care what the square root of x is. So to undo that operation, what we're going to do is square both sides. Square rooting and squaring cancel each other out, and we get x, and 4 squared is 16. And once we get the solution, we need to go back and check and make sure that it is not extraneous. We go back to the original equation. And the thing is, it's this part of the logarithm. That has to be positive. The 2 over here, it's already positive. We could not have worked that out if it wasn't positive. So it's the x. But when we put 16 back into our problem, 16 is still positive, which means that 16 is a solution to our problem. Problem number 15. A nice part is that we have log base 2 for all of the parts of our problem. And as we look at the right side of the equation, we see this minus sign over here, which is going to allow us to use our properties to solve this problem. We can't do anything to log base 2 of x plus 1. But we can deal with the 16 over here. Log base 2 of 16 divided by x minus 5. We have log base 2 on the left. We have log base 2 on the right. That's not going to help us solve. It just gives us like bases. So what we are going to solve is we're going to solve x plus 1 equals 16 divided by x minus 5. Well, we need to get that x minus 5 out of the denominator. So we're going to multiply this by x minus 5. And we're going to multiply this by x minus 5. So our x minus 5 is cancelled out. The other way to look at it is we're cross multiplying with the x minus 5. And now, what we're going to do is we're going to FOIL this. So we get x squared plus 1x minus 5x minus 5 equals to 16. We canceled out those x minus 5's. If we combine like terms, then we have x squared minus 4x minus 5 equals 60. And we're going to have to eventually factor here, and I'm looking to make sure that I did not make a mistake. If we subtract 16 from both sides, then we have x squared minus 4x minus 21 equals 0. And now we can factor. -7 and +3. Again, I hope that you can say x equals 7 and x equals -3. But if you can't, here's the work. We add 7 to both sides, and we get x equals 7. And over here, we subtract 3 from both sides, and we get x equals -3. And then we're going to go back and we're going to check for extraneous solutions. And by the way, it seems that -3 will be extraneous, but we are allowed to have a negative answer. When the value can't be negative is when we go back to the original equation. It's this value that can't be negative. This value cannot be negative. Those values have to be positive. So if we look at our negative, since that's what we're talking about right now, -3, -3 plus 1 is -2. This is extraneous. We ended up with the negative value back in the original equation, and that doesn't fit in our domain. So let's see if 7 will work back here. Well, 7 plus 1 is 8. 8 is positive. 16 is already positive. 7 minus 5 is 2, and 2 is positive. So our answer to our problem is the 7. Problem number 5. So we're kind of jumping around here, but that's okay. Just looking at a couple problems to make sure that we understand what we were doing from our previous day. And it's always hard when you have math one day and then you have a day off, and now we're going to have, after today for this class, we're going to be off until next week, and some of you are celebrating. But on this one, we have to use the definition of logarithm. Remember what we're going to do. We're going to take this 3, and we're going to go around the world here. So this is going to be 3 to the 15 equals 3 to the 4x minus 1. And whether we have a logarithm in here or whether we have some base in there, we need common bases. So we have a base of 3 on the left side, we have a base of 3 on the right side, and because of that, we don't need to deal with the 3's. We need the other part. We need the 15 and the 4x minus 1. And then we're going to solve that equation. We add 1 to both sides, and we get 16 equals 4x. And then we divide both sides by 4. And then it's x equals 4. And you can mentally check this. We don't really need to check for extraneous solutions here because the base 3 is already positive. But if you think about it, we did 3 to the 15 equals this. 4 times 4 is 16 minus 1, and 16 minus 1 is 15. We could type it in our calculator and check as well. Problem number 16. We have 4 logarithms in this problem, and maybe that was where the confusion came from. We have a lot of things going on in this problem, but what I'm going to recommend that we do first is that we take this 2, that's a coefficient of a logarithm, and make it an exponent. So that's my first step. It doesn't necessarily have to be the first step, but if it's not the first step, it probably has to be the second step. This is going to be log base 3 of x plus log base 3 of 3x plus 2 equals log base 3 of 5 plus log base 3 of x squared.
Oh, I messed up right off the bat.
And again, we didn't have to do that the first step, but if we didn't do it the first step, we probably need to do it the second step. Because we need to watch out for these pluses, and on the left side we have a plus, and on the right side we have a plus. So we had log base 3 of x times 3x plus 2. The plus between the 2 logarithms, which incidentally have like bases, can be multiplied. That's what that property says. And then over here, log base 3 of 5 times x squared. This times this. But we now have log base 3 on the left. We have log base 3 on the right. We can ignore the log base 3's. They don't really cancel out. They just don't add anything as we solve. So we have x times 3x plus 2 equals 5x squared. And now we're going to distribute. So we have 3x squared plus 2x equals 5x squared. And as we solve this here, I'm going to move everything to the right side. I know that's not my traditional way, but we're going to have to factor this. And it's much easier to factor when we have a positive x squared term rather than a negative. So if we move everything over, then you get 0 over here on the left side, equals 2x squared minus 2x. And some people made it this far and then had trouble. Some people tried to divide out the 2, but it really can be factored. This binomial can be factored. We can take out a greatest common factor of 2x, and then we're left with x minus 1. 2x times x is 2x squared. 2x times negative 1 is negative 2x. And now we have to solve. So we have 2x equals 0, and x minus 1 equals 0. When we divide both sides by 2, we end up with x equals 0. Adding 1 to both sides, we end up with x equals 1. And they look like perfectly normal answers that would be good. But one of them might be extraneous. Both of them could be extraneous for that matter. We need to go way back to the beginning of the problem. What we're looking at is we're looking at this. Oh boy. We're looking at this x here. Sorry, more disoriented.
That wouldn't work.
When we put 0 back in, is 0 positive? No. 0 is neither positive nor negative. That means that this is extraneous. But when we put the 1 back in, 1 is positive. 3 times 1 is 3 plus 2 is 5. It is positive. We don't have to do anything here with the 5. It's already positive, and we already determined that 1 is positive. So our solution to this problem is only 1.
I cannot do anything correct on that, but I got the right answer.
I don't know how.
I cannot do one thing correct.
You didn't multiply them?
No, I started off with x times 3x plus 2 is 5x. And I ended up having 3x minus 3.
And you missed the 2 completely.
Yeah, I missed a lot of things completely.
Thank goodness Kat had us do it. Are there any more on here? Not that I was completely expecting this many, but whatever.
Wow, I almost wish I had a pen out because I really don't want to erase my answer because although it's wrong, it's kind of amazing that I still got the correct answer.
Hugely amazing.
Samesies.
Alright, oh, it's still on up here.